Yes. Good afternoon. Attendance is already taken as per the list of students available as of now. No more attendance will be taken further. Fine. Welcome to the class. We touched upon mission dependent compiler features earlier. Probably today we should look at in continuation what are those features that we will be having under the concept of a mission dependent compiler features. Hope the screen is visible.
Yes, sir.
Yes. In the previous class, we left at this point of discussion where variance sum SQ 100 minus mean into mean was considered to identify various quadruples that can come under this. And the solution was already given by Sunil, I believe. And the same thing is mentioned here as well for your reference. So we take, as we do normal mathematical expression evaluation, sum SQ div 100 we will evaluate first, later mean multiplication mean, then the result of the left hand side is subtracted using the right hand side, and final result will be assigned to variance. In the same concept, division sum SQ, division is operation, sum SQ is the first operand, 100 is the second operand, and it is stored in intermediate result I1. Next, multiplication is operation, mean and mean are the two operands what we have. The result is stored in I2. I1 minus I2 is the next computation, which is a subtraction, I1 minus I2. Then result is I3. That final I3 will be stored back in the variance. So equal is the assignment operator. I3 is a single operand what we have. The other operand is not required, and hence it is kept blank. Then variance is the destination or the result where we need to have the I3 value. This is how we have done. Similarly, if a program of this category is taken, where only one sentence, line number 14 we have done now. But if you want to write for every sentence, probably you need to write a more number of quadruples, maybe probably as shown like this. So for the program, what is given here with line number 1 to 16, if you start developing intermediate form, you will end up in having these 23 lines. For every line, we will be having a multiple quadruples wherever required, so wherever possible. So this is how we have written. Probably you can refer it later, because we need to understand, like, whatever may be the program size we have, for every program, the compiler will be representing them in the intermediate form. Only when the program what you have in consideration is more complex. If it is a small program, intermediate form may not be required, but the programs of today's nature are very complex in nature, involving so many other parameters. Complex need not be the length of the program. Complexity may be the type of constructs what you have used inside the program. Maybe writing a 10 lines of program, but each line requires so many other facts internally of a given programming language, then that itself is a complex entity. So to devise a best method or optimal method in between, when we have a program in hand, before it is finally compiled or code is generated, intermediate form is normally used or generated. Maybe you can have this as one of the example. While a program is given for a compilation, then code generation for a given program may look like this. So with this probably we'll get into the mission dependent features, which are very important from exam point of view. Okay. So there are two concepts or two ways which we can consider as a part of a mission dependent code optimization. We have some 5 to 6 methods in the mission independent code optimization, but we'll be touching on only 2 of those. But whatever it is, before we get into this, what do you mean by code optimization? Why we need to do code optimization? So we have already discussed in one of the classes, code optimization will only ensure that the program is up to the requirements. It is not containing any redundant data or unwanted data, which probably will help us to save the data which we are going to keep for the object program, maybe in terms of its length or in terms of the time required for execution. That is basically called as a code optimization. But coming to our programming languages, code optimization should not be looked at as removing the redundant data alone. There are certain situations, even though some data is redundant or some data is not used, it need to be protected. Remember the word, it need to be protected. Normally, we mean optimization means remove the unused data, or remove the unused instruction, or remove the content which is not that important in a given programming language. We keep doing that. Normally when you write a program, there are some situations probably where some data is declared but never used. There may be some instructions where redundancy is there, we can replace them with an optimal instruction. All those things are possible. So normally optimization means removing the things which are not available, which are not required. But at the same time, code optimization also deals with some aspects where even though things are redundant, may look redundant, even though some values are not used in the given program or context, they need to be protected. That is also an example of a optimization. So any examples for that, where whatever the data we have kept in the program, even though it is not used at the given point of time, that data should not be removed. The data should not be optimized in our normal words. If that is the case, can you give me an example? What could be that data from a programming perspective? So what I am asking here is, normally the data which is not used but declared in the program will be removed. That is optimization, because it is of no use. But there are some situations where even though the data is declared, even if it is not used in the given program, but it need to be protected for some purpose. Do you have an example of such data, or do you foresee such data is required in a given programming language, or have you come across any of that category all these years? So may get some. Pardon?
Comment line, sir.
Connect.
Comment line, comment.
Comment line. Okay. That means you don't want to remove comment lines?
Remove, sir. We can.
No, comment lines will never participate in the object program. Comment lines only for us to read the program. Comment lines in any language will not be participating in object program. So that is not possible. So comment lines will not be part of it. Any other things? Where the data you declare, but you may not be using that particular time, but the data is prone to changes during runtime, let us say, which compiler may not be aware. Compiler simply removes it from the program, thinking that it is nowhere used in my process of syntax analysis or lexical analysis. But you internally feel that, no, it should not be removed. There is something in future where my data is going to be updated or is going to require some activity. But how do you inform the compiler if that is a requirement? Or first of all, do you see the need for such things? If it is so, have you used them already or not? What it can be? Any other inputs?
Sir, like in general or what?
Pardon?
In general sense or what? Sir?
Central sense means?
General sense.
Or
Or what,
general.
sir?
No, do you see a need for such things where you declare something and normally what you declare you should be using? That is the fundamental rule, right? For example, you declare int sum for some purpose, because when you write a program, this is possible, but you never use that sum in the program. And when you compile, probably you will get a message warning from any compiler, C, C++, Java, that you have defined it, you have declared it, but not used. And we ignore that. When we ignore that, what will happen internally? Compiler will not ignore that. Compiler will remove that, because anyhow you have granted permission for me, telling that it is declared but not used. But compiler will not keep them those type of things unnecessarily, which is a burden. It will silently remove without your notice. That is called as a code optimization in general, because removing unwanted requirement of data which is done maybe by mistake by the programmer, but compiler is wise enough to remove that. That is one part of the story. The other part is, okay, you have declared, but you have declared with a purpose. Okay, during that program it is not done, it is not required, but I am working on a big program where the whatever I have done in this current program is required by another program, let us say. Maybe such situations of reality, we may declare something in the current program, but compiler will not think no as we do, because compiler means it will look only at the current program. It will not connect the current program with other program unless we dictate it. In such situations, you may require some data which you have kept, or maybe within the program you have kept something which is going to be updated during runtime, not at compile time. Again, compiler will not be knowing that what is going to happen during runtime. But such things, if you, first question is, do you foresee the need for such things in a programming? If at all that is the case, how do you protect them from not being removed from the system or not being optimized by the compiler? These are the two questions what I have with me now. First of all, is it need? Is it required? Do you see anything where yes, there is some requirement where I have some program and that program contains something which is not used at all, but I should not remove that, it is required for some other purpose? What about volatile qualifier? Have any of you heard about volatile qualifier? None of you? Have heard about volatile or not? Constant qualifier, volatile qualifier. If you are not heard, means you are not studied C++. As simple as that. May I have some answers? No answers? Okay, let us come to our discussion. Fine. So code optimization now is mainly to improve the efficiency of the program. So what do you mean by efficiency here? A program efficiency can be measured in two cases, maybe time as well as the memory, which you have been aware of it as far as ADA is concerned. The same holds good here as well. So time of a program should be reduced wherever possible so that execution takes less time. At the same time, memory of a program should not take more memory it should take less memory. But we cannot remove the content of a program, but nevertheless, we can avoid the redundancy. If at all anything is existing, we can make sure that the program run faster because it has a less content. This less content more so depends on the redundancy of material that we have in the program and being removed from the program. So code optimization majorly is a task for a compiler to ensure that what is relevant in the program is there, what is irrelevant in the program is removed. The simple words if you want to take or tell about the code optimization. To guarantee that, there are two approaches now which we can look at as a mission dependent code optimization methods. First, dividing the program into basic blocks, which will help the program, the compiler, to understand whether optimization can be performed in this direction. Second way is rearranging the quadruples. These are the two very important and critical things in the optimization process. And let us see how this is being accomplished. So dividing the program into basic blocks and rearranging the quadruples. Before we get into this, so code optimization, one side is making the code which is efficient in terms of its length and it's in terms of the time taken for the execution. So in terms of time taken for execution can also be depending on the runtime, because every program that we have given, we know from computer organization perspective, it has to go to the RAM, and from RAM it will be executed in the processor, and processor is more responsible to making sure that the program execution is complete. In that process, when the program is sent to the processor, all those units which are registers, your IRs, PC, control unit, ALU will all together will ensure that the program is executed successfully. But there, unless there is a proper coordination among these units, you will not be able to do that. Even if there is a proper coordination, the data what is required for a program, maybe instruction or the input data, if it is not available, again the program is not going to efficiently execute. So what we are trying to discuss here is, one way is making the code, object code, more efficient by removing the redundant portions. At the same time, to increase the efficiency of the program, there may be some issues at runtime which we need to take care. And those issues at runtime may be with respect to the how do we storage the intermediate values or the values which are required for a very small amount of time, which are there for a very limited period of time. And this is going to be a more critical point for any compiler, because the number of registers what we have in a processor are very, very limited. Even if we have a 10 registers, in that 4 or 5 may be reserved for some purpose. We have seen already in SICXE, even if we have 9 registers, only 2 registers are in our disclosure. Remaining all 7, they have their own purpose. We cannot touch them. Out of 9, I am left with 2, that is S and T, where I can play with them. Others are not for me because they have their own intended purpose. So if that is the case, these registers are going to be more important, because registers are very much closer to the processor by proximity of their availability, and execution takes very less time. So if at all I need to make a program more efficient in terms of a time taking requirement, probably I can look at the concept where is it possible to have the data in processor only and make sure that processor completes all these required executions or computations quickly, so that the time taken for the data transfer between RAM, between processor, between RAM and the processor, or between RAM and the secondary memory. If I can reduce the transaction of data, probably we can talk about that we are going to have the more optimal execution of the code or more efficient program being executed. So what we are talking here is, at runtime, is it possible to depend more on the registers of the processor rather than the secondary memory or RAM? By doing so, the transfer of data between RAM and processor, or RAM and secondary memory can be reduced to the extent possible. In other words, can be optimized. So your optimization meaning here is that in the processor, let us use the registers which are available. No doubt it's a good option, but availability of registers in processor is a big deal, because as we know, first of all, there are less number of registers, and those registers all are not in our discretion. Only few, maybe 20-30% are available. But how efficiently we are going to use those 20-30% is what is going to decide whether I have got a optimized program or not. So optimization from the compiler perspective, there are multiple ways we have to look at. One is from the physical code what we have, which that means you are translating a given programming language to the object program. Of course, that is also required. At the same time, during runtime, is it possible to reduce the dependency on either RAM or the secondary memory as far as the storage is concerned? In other words, can I make use of the registers of a processor in a better way? If that can be done, again, probably we can ensure that optimization of the code is possible. That is the idea behind here. As far as the code optimization is concerned, it doesn't matter whether we do dependent of compiler, machine architecture or not dependent, but this is the main idea. That means, is it possible to have more processor registers, or is it possible to use registers of a processor in more wider way, so that the dependency of other things, that is RAM and secondary memory, can be reduced? If that is something can be identified, probably we can achieve code optimization in real time. So that is the idea behind what we are discussing today. Maybe the code optimization from mission dependency perspective, we have two things. One is arranging them into basic blocks and rearranging the quadruples what we have for a program. So first thing, let us see dividing the program into basic blocks. Whether it is dividing the program into basic blocks or intermediate quadruples being reshuffled or rearranged, or what you see later under mission independent code optimization, in all these cases we are worried about, or we are aimed at rather, can I reduce the dependency on RAM and secondary memory as far as the computations are concerned? Or in other words, can I make use of the registers of a processor in a big way, so that I can reduce the time taken for the program execution, thereby I can bring an efficient or an optimized program. So that is the perception with which we will be looking at this now. Let us look at the first concept, dividing the program into basic blocks. So a block, we know, a module is a group of instructions which we are going to consider. In our case, since we already have some quadruples with us, and we can consume that this group of quadruples are going to be a block, and each block will have an entry and exit, because you cannot simply block instructions of a program as we want or with a specific number. No, whenever you are going to group certain things, obviously we know even in our own programming language we put some group of instructions wherever there is some link or some relation. Otherwise we will not be doing that. The same process, a block here in the quadruple grouping will also have starting point, will also have some ending point. And no group will involve loops, in the sense, suppose I have constituted 5 instructions as a block. Out of these, every instruction is an independent instruction. No instruction will have a jump for another place or a call for another place. No. So they are going to be very normal instructions, very general instructions. So any loops or jumps or branches will not be part of a block. That means if at all there is a block, or if at all there is a jump instruction, if at all there is a branching instruction in a given program, then probably that need to be considered as a separate block. That is the meaning here. So we are going to divide the program. We means the compiler is going to arrange all the quadruples in terms of groups, and each group is going to be called as a block with 2 restrictions. What are they? The block should have an entry point and an exit point. Second, block should not have any looping or branching statements within it. So quadruple will have an very completely independent set of instructions, maybe interdependent, but not very far away from the block. So what is going to happen by doing that now? So by doing that, we are going to make sure that we know that our programs are sequential in nature. When I have some data in my first 10 statements, I may be using them in the 11th statement or 12th statement and program which is there in the further side. If that is the case, whatever I compute in the first block may be used in the second block or third block or fourth block. By doing this, what I can do is I can reuse the data what is already there in the first block, maybe in second block or subsequent blocks. So reusability is what something we are going to achieve. Second, since we have the registers available wherever possible, we can store them in the internally processor. So when a next block comes for execution to the processor, I can reuse rather than sending them back to the memory and bringing it back to the processor. So these are the two things probably which we can look at as an advantages as far as the dividing the program into basic blocks are concerned. So one, to reuse the data which is there in one block in other blocks. Second, while doing the reusability of data, make sure that the data is stored in the registers of the processor than pushing it back to the secondary memory or RAM. So that is the advantage here. So even one instruction, if we can do that, it is going to help the system or the program to enhance its efficiency. Okay. Take this program, which is just now we have converted into quadruples. It's a very big program. Let us not worry about that. But let us see how this can be grouped into blocks. So probably if you look at line number 1 to line number 23, anything which is having the rules. What are the rules for a block? Each block should have a entry point. Each block should have a exit point. Same time, there should not be any branching and looping as far as the block is concerned. If you start from line 1 here, this line is assignment, assignment, assignment. So probably I can group all these three into one block because there is no branching here. But when I come to fourth line, there is a branching. There is a branching, jump. Next again, there is a call, value, all this if you see until 13, there is no jump here. I can probably group them into a block. So next again, there is a block, which is a jump. Next I have all these again till I call some program. So like this, we can identify various blocks which pertain to the definition of a block. So if you look at the consequence of blocks that can be identified for this. So line number 1, 2, 3, I can keep as one block. Whereas from line number 4 to 14, JGT till 13, I can have one block like that. Let us look at how this can be done. So observe here. So 1 to 3, one block, 4, one block, 5 to 14, one block, 15 to 20, another block, 21 to 23, another block. This is not written out of fancy, but just now we have seen 1, 2, 3, I can make one block, 4, a separate block, then I have a call for X read, it will come up to 14, that is 5 to 14, it has one loop here because J4, we are going back to the 4 here. Why it is 4 up to 14? If you look at that, result is going to line number 4. So JGT, J has some link here, so J4, so 14, then again 15, 15 to 20, 15 to 20, then 21 to 23. And these arrows, we'll talk about that depending upon the looping. So when you come to 5 to 14, again you can go back to 4. Again, when you are at 4, you can come back to 15, like our if-else statement. So this arrow marks will show. That is not our concern here, but our concern here is how we are going to divide them into blocks so that each block is independent. So you need not execute them again. Suppose if you want to use the data, what is there here, I can use it here. So if that is the case, probably we'll be able to make use of reuse concept of data what is there. So thereby we can reduce the executing or computing the same program or same construct again and again. So this is the concept of grouping the given quadruples or the given program into blocks. And these blocks are independent in nature. They will not be depending much on others except reusability of the data. So this is what for this particular program we can write like in the exam. Probably can show an example of this category and make sure that these blocks are going to be of somewhat helpful in code optimization from a mission dependency perspective. So if we look at the other concept, which is rearranging the quadruples, that is very important. We know the quadruples. For every statement we keep writing quadruples. We have written a couple of quadruples in the previous class. We take this value is equal to a plus b into c minus d. So quadruples for this are like this. How we are going to write? First multiplication b into c, then a plus b into c, then minus d, then assign. So first multiplication, then addition, then subtraction, then assignment. So here we know that first I need to compute b and c. So b and c data is stored here as I1. Next I need to compute a plus b and b into c, which is stored as I2. Then whatever I have here as I2 minus ID. So I2 minus ID. I2 is already there in the processor minus D, which is available here. I will get I3 and I assign. So it is very straightforward. There is no much rearrangement is required here. So what do you mean by rearrangement here before we get into the rearrangement concept? Assume that now I have I2 here. I have computed by a plus b into c. After that I have a minus d. When I compute I2, we know that any recent computation will be stored in the processor register or maybe in the accumulator or maybe it is available in a given place which is stored just now. When I want to perform something minus something, please understand here, when I want to perform some subtraction, the left hand side should be always available in the position so that I can only subtract the right hand side, that is the subtrahend from the given value. If that is the case, I2 is already there and from I2 I am going to subtract. Assume now it is a reverse process. Just now I have calculated something. So this is I2, let us say, instead of I1 I have I2, this is I1. Just understand what is the concept of a rearranging. So I2 is computed in the first place, I1 is computed in the second place. Now my requirement is I2 minus D. But where is I2? I2 is not in my immediate custody. It is already created, already computed, stored somewhere. If it was immediately computed like what we have discussed just now, I would have no problem. But now I2 is required, but I2 is not immediately computed. What I have to do now? Whatever I1 I have here, that will be pushed back to the memory. Wherever I1 is there, that will be brought back to the processor. So what is happening here? Before I compute my subtraction operation, I need to bring this data wherever it is to my processor if it is not already there. If it is already there, I can avoid that process of data transfer. If it is already there, I need to be using them directly. If it is not there, then I need to bring them, which may incur in one more data transfer. Probably may not be able to appreciate here. Let us take one more example, which is a regular div example variance. We will see what is the rearranging of quadruples. So meaning that by rearranging the quadruples, you are going to reduce the data transfer that is unnecessarily required between the processor and memory or vice versa. So is that really is going to make some sense? Yes. Let us take an example here. Take our example of variance, which is defined as sum is equal, variance is equal to sum by 100 minus mean into mean. You all know that these are the quadruples for it. Any doubts here? Please let me know. We have computed division, sum 100, I1, mean into mean, multiplication, mean into mean. Then left hand side minus right hand side. Where is left hand side? I1 here. Where is right hand side? I2 here. I1 minus I2, I3. we got the result. Absolutely no problem, we got the result. But there is a scope here for the possibility of rearranging of quadruples. By rearranging quadruples, you should not lose your focus. What is the focus? I need to compute variance. Just because I want to rearrange, that doesn't mean that I'm going to compute something else. No, your data which is there in the left hand side still need to be computed. Rearrangement is only for the burden of a processor, where processor unnecessarily involves in the data transfer, which otherwise could have been avoided. If that is the case, probably we can do that. So if you see here, first I'm calculating I1, next I'm calculating I2. In similar lines, what I've discussed here, if you come here and observe or apply I1 minus I2. But I1 minus I2, where is I1? I1 is not in my processor as of now. It is somewhere, it is not in the accumulator. So what I need to do now? I need to bring I1 back to accumulator. So what will happen now? Whatever I2 I have, I need to store in some other variable. Whatever I1 is there, I need to bring it back to accumulator. So two data transfer instructions are being used here, which are waste for me. If at all I can avoid them, these two instructions, which can be further reduced, we call it as an optimization in our case, then probably I need not. For us, it looks very simple, very plain. Okay, I1 minus I2, I3. But look at from the processor perspective. I1 is not here in the direct computation. It is done yesterday, let us say, in previous instruction. That means it is not part of the accumulator. But I need to bring it back to accumulator because I am going to subtract some data from it. So data transfer is extra. Not only that, we have some data in accumulator. I cannot lose that. I need to push it some other place. So two data transfers. One, existing accumulator data to intermediate place, and whatever is there in I1, bring it back to the accumulator. So these are the two extra instructions, extra computations rather, which we can avoid. That is the concept of a optimization. So how do we do that now? So what we can do is we can rearrange the quadruples. How do we rearrange? We have computed division first, we have computed multiplication first. Rather than that, can we interchange this? That means compute multiplication first, then division later. With that, what will happen? I1 will come to the second line, I2 will be in the first line. So I1 is already there in the accumulator. I need not do any data transfer. Simply I can get the I2 data alone back to this. So instead of two instructions, I'm going to do only one instruction, that is getting the data of I2. Right? If that is the case, we are going to reduce the dependency on the data transfers from 100% to 50%, and that is going to ensure that data is going to take very less time for the transfer. And obviously, this shows that code is getting optimized. So by rearranging the quadruples, what we have in the program, we can achieve the possible optimization. It may look very simple, but this is just one example. If you take a program in real time, programs will have multiple things of this nature. So compiler is doing for us in the background that can I reduce this dependency? Can I make sure the program is more optimized? So let us see what is the solution for this now. Okay, now this is the solution. Instead of computing division first, I'm going to compute multiplication, where I give I2 for this. Next, I will compute division, then I'll get I1. Now I1 minus I2. In the previous case, I2 was here, but I1 was required. So we need to do data transfer. Now I want I1. I1 is already there. So if that is the case, I need not do any data transfer. It is already there in the accumulator. Only thing is I need to bring I2 and subtract, get the result I3. Once that is done, by rearranging these two, which was division first, multiplication earlier, right? Now we have rearranged. By rearranging that, that is multiplication first, then division, that is rearrangement. We are able to reduce one computation in what is that computation? Data transfer instruction between secondary memory and processor. We are avoiding that. Okay, that is the case. We say that we have a rearrangement of quadruples, which is giving room for the optimization of the code. So that is the concept of a code optimization. We are looking at it. So first one is dividing the blocks, where reusability will be the important concept. Rearranging the block, where once again the processor data need not be sent back to the memory and vice versa, which we can avoid by rearrangement. So this is how the code optimization can be visualized or brought into the system. So this is the concept of a code optimization. So we'll stop at this point of time today, which is code optimization from mission dependency perspective. Next topic probably will take up on the code optimization on a mission independent feature concept. So any doubts at this point, probably can let me know and wind up. So this is what just I'm showing, which I've already shown. I'm just showing in a better way. You can see here also the code. What is the result of this? How many sentences it contains? 1, 2, 3, 4, 5, 6, 7, 8, 9. Here you can see after rearrangement 1, 2, 3, 4, 5, 6, 7. So 2 instructions we have reduced. So one for storing back to the memory, second bringing from memory to the accumulator. So this is the optimization. Why it is possible? Because we have completed multiplication first, which was earlier division. So which was division earlier has been replaced by multiplication. So we have rearranged these 2 quadruples. So which reduces obviously in the code that we are going to generate. This is an example of a code optimization. Stop if you don't have any questions here. We'll get into the mission independent features in the next class. Attendance already taken, because I've been observing students are not participating in classes. So I've taken attendance based on the participants in the first 5 minutes, and no more attendance can be taken. Thank you. If you don't have any doubts, you can leave.
Hello, sir.
Yes?
I am Sunil, sir.
It's okay.
Okay, sir.
I'm not doing any attendance. I've given attendance in the first 5 minutes. Since nobody was there, only 20-25 students were there, I've given attendance to them.
Sir, network issue got, sir.
It's okay. Daily it cannot be the problem, because I've been observing. I've been patient and I've been warning.
No, sir, today
It's okay, fine. You attend hours regularly. Okay? Be on time. Thank you.